In this video, we're going to look at Chapter 18F on trigonometric equations. We're going to solve equations using sine, cosine, and tangent of theta. Before we do that, however, let's take a look at a few things that we've learned in previous sections. First, consider these 2 points on a unit circle, formed by this angle and this angle. The first point has coordinates A and B, and the second point has coordinates negative A and negative B. Remember that these 2 points are going to have the same sign because they both have the same y coordinate. We have the same y coordinate, so we have the same sign. Let's take a look at another 2 points, one in the first quadrant and one in the second quadrant, and notice that they have the same x coordinates this time, which means that they're going to have the same cosine because they have the same x coordinates. Here, one last case. Again, we'll take the same first point in the first quadrant, and then we'll take a point in the third quadrant. And notice that I don't have either the same x or same y coordinates, but I do have their negatives. And in this case, these 2 angles are going to be 180 degrees or pi radians apart. So this first angle is going to be 180 degrees away from, or pi radians away from, this angle. Now, when we're trying to solve trigonometric equations, for example, let's say we have the sine theta equals 1/4. If I'm trying to figure out what theta is, it's often useful to use a working angle. And a working angle is an angle that's located in the first quadrant and it's symmetric in some way to the angle that I'm interested in, or angles, and it's derived from the modulus of our given ratio. In this case, our given ratio is 1/4, and the modulus is sort of like the absolute value of that ratio. Now in this case, 1/4 is already positive, so I actually don't really need to change it. But sometimes I'll have a ratio that's negative, and I'll need to use the modulus to find the working angle in the first quadrant. And that will become clear as we go through a few examples. Our first example is sine theta equals 1/3. This is a pretty basic trig function, but it will help to illustrate how to use a working angle to solve these equations. First thing that we should do is draw a unit circle. Next, let's take a look at the ratio that we've been given, 1/3. 1/3 is positive, and I'm trying to solve an equation using sine. So I know that sine is positive in the first quadrant and second quadrant. That means my 2 answers are going to be here or here, and that's not to scale, it's just a guess. But we'll use the working angle to give us some more exact calculations. Also, since our ratio is positive, our working angle, which we'll call alpha, is going to be one of our solutions to this equation. And I don't really need to do much different to find alpha. I just need to set up an inverse sine. So theta equals inverse sine of 1/3. And I can plug that in my calculator, and I will get approximately 0.3398. And that's my working angle alpha, but it's also one of my solutions because they're both in the first quadrant. Now remember that this point over here has the same y coordinate and therefore the same sign, and is also an answer to this equation. So I need to find this angle. Well, because they're symmetric in the first and second quadrant, I know that this angle right here is also alpha. And I know that if I go through 1/2 revolution in radians here, I've gone pi radians around the circle. So to find this angle, I simply need to subtract my alpha from pi. And pi you can plug into your calculator or you can approximate it. But if we do that, we find that our second solution is 2.802. Now we will almost always get two answers in these trig equations. But remember that your calculator only ever gives you one answer. And usually, if we set up our problem right using the working angle, or the modulus of the ratio, we get the working angle, which is in the first quadrant. That may or may not be one of our solutions. So we need to use symmetry here in the unit circle to find our two solutions. Let's take a look at another example like this. We're going to solve the equation tan theta equals minus 2.179. Again, we're going to set up a unit circle, and using the modulus, which again is the sort of the absolute value of this ratio, this number over here, using the modulus, we're going to solve for theta using the inverse tangent. So notice I'm using a positive 2.179. If I plug that into my calculator, this is actually alpha. I'm going to find my working angle alpha, which is 1.1405. And so that's this angle right here, alpha. Now because I'm dealing with the tangent, or the ratio I'm given for tangent is negative, my answers are actually going to be in the second and third quadrants. That's because tangent is negative in the second and fourth quadrants. So I need to set up my unit circle and to find the other 2 points, or my two answers, using symmetry. And we know that this guy right here is also equal to alpha, and this guy right here is also equal to alpha. So if I want to find this angle and this angle, I see that the first one is simply pi minus alpha, and the second one is 2 pi minus alpha. And so all I need to do is plug in alpha, and I come up with one solution for theta is approximately 2.001, and the other solution is 5.143. So again, the first solution is 2.001, and the second solution is 5.143. And that comes from just a little bit of geometry and logic from the unit circle. Now let's take a look at a slightly more complicated example that involves a little bit of factoring first. So this is a trig equation, but it's obviously a little bit more complicated. So sometimes I'm going to need to factor first and then solve for theta using the methods that I just showed you. For example, here I could subtract sine theta from both sides of the equation to get 0 on the right hand side, and then notice that each of these terms has a sine theta, so I can factor that out. And I'm left with this. And from here we need to recall some information probably from Algebra 2. And I'm going to switch over to substitution here. If I were to give you an equation like x times 2x minus 1, you might remember that I can solve this equation, or that I'm going to get two solutions from solving this equation. Either this first term needs to be equal to 0, or the second term needs to be equal to 0. This is the product rule. One of these two terms has to equal 0 in order for this equation to be true. And in fact, both of them, we're going to solve both cases. X equals 0, or 2x minus 1 equals 0. Well, the first one's already solved for us, and with a little bit of algebra, the second one would be solved as x equals 1/2. Now, let's do that without the substitution. Let's do that with the signs still in there. So we're going to have sine theta equals 0, or 2 sine theta minus 1 equals 0. Now again, the first problem, we don't really need to do much, because I don't really need to use working angles here to solve this equation. I know that sine theta equals 0 occurs at 3 places on the unit circle. Once at angle 0, once at angle pi, and once at angle 2 pi. And those are 3 possible solutions for my equation. Now on the right hand side, I need to again use a little bit of algebra. So I'm going to have sine theta eventually equals 1/2. And here I need to use working angles. So I can set up a unit circle really quickly. I'll just sketch this one out. And because I have a positive sign, I know that my answers are going to be in the first and second quadrant. So my working angle alpha is actually going to be one of my answers. Take the inverse sign to find alpha. Inverse sign of 1/2. Okay, and that's going to get us an angle of 0.5236, and we know that our second solution is going to be pi minus alpha from the unit circle, right? This is alpha, so to find this angle I do pi minus alpha. And that's going to get us 2.6180. Now, we could have noticed that sine of 1/2 is one of the common coordinates from our unit circle, right? In fact, our first answer here is really pi over 6, and our second answer is 5 pi over 6. But I wanted to go through the process to show you how to use the working angles again. But if you recognize that sine theta equals 1/2, we could have been solved from using the unit circle, then that's also a valid a valid solution. So notice that I have 5 overall solutions here to this problem. And that's okay. Alright, let's look at one more example really quickly to practice a little bit more factoring, and then we'll be done. Okay, in this equation, we're given 3 cosine squared theta equals 2 cosine theta plus 1. Again, I'm going to solve for 0 on the right hand side. And that isn't always going to work, by the way, but it's a good first step. And then I'm going to see if I can factor here. And remember, if you need to use substitution, you can. Right, 3x squared minus 2x minus 1. That can be factored to 3x plus 1 times x minus 1. And then when you're ready, just substitute cosine theta back in for x. So I'm going to have 3 cosine squared theta, or sorry, 3 cosine theta plus 1 times cosine theta minus 1 equals 0. And now I have 2 separate scenarios that I can solve. 3 cosine theta plus 1 has to equal 0, or cosine theta minus 1 has to equal 0. I think you'll see that on the right hand side. That one's pretty easy to solve. Let me get rid of that. We have cosine theta equals 1, and we know that to be true at 0 and 2 pi. So I don't need to use working angles here. On the other hand, on the left hand side, we have cosine theta equals negative 1/3. And here I'll have to use working angles, keeping in mind that we have a negative ratio, so I'll have to use the modulus first and then use symmetry. If you go through that process, which I urge you to do, you should get theta is approximately 1.911 or 4.373. And those are your 4 solutions to this problem.